Now that we've refamiliarized ourselves with some of the terminology surrounding solutions, let's go ahead and start talking about why do solutions form. So we really want to talk about this like dissolves like concept or principle. This is based on intermolecular forces. The intermolecular forces, though, specifically between solute particles and solvent particles. Why does a solution dissolve? Because they want to interact with each other. That's what I mean by things like dissolves like. A polar compound will dissolve in a polar solvent. A nonpolar compound will dissolve in a nonpolar solvent. Polar solvents are not going to dissolve a nonpolar compound. They don't like each other. They don't want to be around each other. So you should be able to use your solubility rules, like dissolves like, to predict if two substances are likely to be soluble in each other and understand the enthalpy components, delta H of solution, and why a solution process is endo or exothermic. So it's a little bit more terminology here before we jump into the process. Solvation. Solvation is the clustering of solvent molecules around the solute particles. That's what causes it to dissolve. We've talked about this with sodium chloride here, and we see like this sodium ion here is being solvated by the water molecules. Hydration is a specific term where it's solvation if solvent that you're using is water. So we say it's been hydrated, or it's a hydration process if the solvent itself is actually water. We use water as a solvent all the time. That doesn't mean it has to be the solvent. We're going to see examples where water is not our solvent. So you need to understand that it doesn't have to be water. But if it is water, we can also call this the process of hydration. As a reminder, energy is required to break the solute's IMFs and separate it into smaller pieces. There is a reason that these particles are held together. There's ion forces here. They're ionic compounds. They're anions and cations that have an opposite charge attraction to each other. Energy is required to break apart that attractive force. Energy is also required to break apart the solvent's IMFs to allow room for the solute pieces to enter. If I have a bunch of water molecules, these water molecules form hydrogen bonds. I need to be able to break apart this interaction to allow the water to hydrate or solvate the ions themselves and dissolve that solute into that water solvent. Energy is released when the new IMFs are formed between the solute and solvent. So the interactions here, these are the interactions between your solute and solvent. When those are formed, energy is released. The solution process. So an important question I want to ask you is, what is the driving force? Why does this happen? Why does something dissolve? Why doesn't it just sit there forever? Or why does it not dissolve? That's also happening sometimes too. But let's talk about when it actually does dissolve, when it forms a solution. Why is this happening? This comes back to the solubility rule of like dissolves like. What this means is that polar solvents dissolve polar and ionic solutes. Hydrophilic groups like OH, CHO, C double bond O, COOH, NH2, Cl. These are hydrophilic, meaning water-loving. And remember what these look like. OH, CHO would have an R group over here. A CO, it's just a C double bond O. COOH has a structure like this. NH2 Cl, etc. Nonpolar solvents dissolve nonpolar solutes. These are hydrophobic or water-fearing. So like carbon-hydrogen, those are nonpolar. Carbon-carbon bond, nonpolar. Iodine-iodine, nonpolar. If I have a nonpolar species, realize there's no difference in electronegativity there, meaning it is nonpolar. So remember, how does our electronegativity will lead into polar or nonpolar bonds. And if I add this to molecular geometry, I can determine is the compound polar or nonpolar. We also have what we call immiscible immiscible substances. Immiscible is when the solute-solvent interactions are not strong enough to overcome the energy required to separate the solute and solvent particles. Basically, the solute and solvent will not mix. And that's what I see happening here. There's an interface between them. This is nonpolar. This is polar. In order for that solution to mix, I first have to break up the attractive forces between each one of these particles. So I have to get these things alone. What IMFs am I talking about for nonpolar? London dispersion forces. Remember, LDFs are the weakest force, but they can become pretty strong as the molecules get larger and larger because of polarizability. I have to break apart all of that attractive force, all those LDFs based in the more polarizable the compound, the stronger those forces become. For water, water's polar, but it also undergoes hydrogen bonding. So I have to break apart all those hydrogen bonds as well, and then have an IMF, intermolecular forces, take over between that pentane and that water that's stronger and can overcome the difference in the energy required to break them apart from their individual species to form that solution. That doesn't always happen. And if it doesn't happen, it's again, the solute-solvent interactions are not strong enough to overcome the energy required to completely separate the solute and solvent particles. So to understand the driving force in the solution process, we need to think about three factors. We've got intermolecular forces, entropy, and the energetics or enthalpy of your system. And here to help us learn about driving force, this is Lily, my daughter's cat, and she was helping us demonstrate the driving force of a reaction. So again, let's go ahead and see. We know we need a driving force. The driving force meaning why does the reaction go forward? And you're looking at these three pieces: IMFs, entropy, and enthalpy. So your IMFs. Going back to your IMFs, I need you to understand the IMFs that are occurring between the solute and solvent particles in the solution. Solubility is completely dependent on these attractive forces between the solute and solvent molecules. Many molecules contain hydrophilic and hydrophobic pieces, so solubility actually becomes a competition between them. Again, hydrophilic meaning water-loving, hydrophobic meaning it's nonpolar or water-fearing. We say like dissolves like because the formation of IMFs or intermolecular forces between the solute-solvent provides the energy to break apart solute-solute and solvent-solvent interactions. Oftentimes when I get students in, say, organic lab, they'll ask me, what solvent should I use? Or how should I dissolve this? How should I recrystallize this? I don't know what solvent to use. I don't know what's a good one. And I'm like dissolves like. What do you have? Is that polar or nonpolar? Like dissolves like. We do have 6 forces that you are responsible for understanding. We have ion dipole. An ion dipole is just that. It is an ion with a compound that is polar or has a dipole. In this case, we're showing you water. Water is a dipole compound, but it also is hydrogen bonding. Yes, we know. But it's a dipole. So we've got your ion here, and we've got your dipole. Dipole again meaning polar compound. So sodium chloride in water is a perfect example of an ion dipole. Ion dipole, again, you've got an ion, And then you've got a compound that has a permanent dipole in it. So we don't say it, but this is a permanent dipole. We can also have hydrogen bonding. Hydrogen bonding doesn't have to happen just between a compound by itself, such as water hydrogen bonding with itself. Hydrogen bonding can occur between different compounds. The rules are the same. You need a hydrogen bonded to an oxygen, nitrogen, or fluorine, and it will form a hydrogen bond with a lone pair on a different oxygen, nitrogen, or fluorine. So in this case, we show ethanol with water. Ethanol and water actually mix better together by themselves. If I was to take a graduated cylinder with about 5 mils of ethanol in it, I took a second grad cylinder and put about 5 mils of water in it. Let's say I put exactly 5 mils, so I'm actually measuring these things out. When I mix them together, so I have 5 mils here, 5 mils here. People assume I should have about 10 mils here, right? What you're actually going to find is you're going to get 9.5 mils of total solution. Water and ethanol like each other so much, they fit together better than they do by themselves. They fit so well together because of the IMFs holding these solutions together. So hydrogen bonding again can occur between different species as well. We have your dipole-dipole forces. This is this concept again of like dissolves like. These are compounds that have permanent dipoles. And so propanal and fluoroform, both of these are polar compounds. They both have a dipole. Propanal is dipole towards this oxygen, or partial negative here, partial positive here. Fluoroform gives you the partial negatives towards the fluorines, which means I have a partial positive charge here on this hydrogen, and I'm going to form a dipole-dipole interaction between these two compounds. That is a driving force. That is an interactive attractive force that drives this reaction to form and dissolve, forming a solution. We have ion-induced dipole. An ion-induced dipole is where an ion induces a dipole in a nonpolar species. So chlorine forms chloride. If its chloride is an ion, it's a Cl minus, it has one extra electron, which means this has a negative charge to it. It's going towards heptane. What it does is it's going to force the heptane to push all of its electrons away from it. Chlorine, again, gains one electron, forms chloride. Chloride already has an extra electron. That means the electrons in heptane don't want to be near it. It's going to push all of its electrons over here, causing a partial positive charge over here. This is an ion-induced dipole. This is actually how O2 gas works in hemoglobin. So we've got iron 2+, and it bonds to an O2 molecule. The iron is a 2+ charge. This oxygen takes a negative charge. Let's draw that so you can see the color. This oxygen takes on a partial negative charge. This oxygen takes a partial positive, but it forms an ion-induced dipole to hold that oxygen onto that iron group. We have dipole-induced dipole. In this case, we see we have a polar molecule and a nonpolar species. These can be molecules or individual species, but this oxygen has a partial negative charge, so it's going to force the electrons to this side of this polarizable molecule, which is going to give it a partial positive over here. And then dispersion forces, London dispersion forces work the same way. as they do. If I just had decking by itself just undergoes London dispersion forces. If I mix decking and octane, same thing, London dispersion forces. And remember, polarizability comes into play. The more polarizable the compound, the stronger those forces will behave. Even if they are just an LDF, which is the weakest force, they can still pack a pretty good punch because there's a lot of that interaction going on. We also have entropy. We will delve more into entropy in, I believe it's chapter 17. I'm not positive on which chapter that is, to be honest with you, but it's the thermal chapter. I might be wrong on that chapter number. I can't remember the chapter numbers off the top of my head right now. And I think it's actually chapter 18 or 19, maybe even 19. But that's not the point. It's going to be the thermodynamics and free energy. Entropy, though, is a measure of the disorder or randomness of your system. I say entropy is a measure of the disorder. That's not completely incorrect. It's not the best definition. The best definition of entropy is the number of microstates the system can exist in. But that leads to disorder or randomness. It's the number of arrangements, positions, and or energy of a given state. So more positions, more energies of a given state, that leads to more disorder. That is positive entropy. Entropy wants to be more states. The more states something has, the more disorder it has, the more favorable it will be in. The more favorable it will happen. So for entropy, this increases as the number of energetically equivalent ways of arranging the components increases. It's a dispersal of energy. If I can hold, imagine in your hand, you cup your hands together and you're holding a little pot of energy. That pot of energy is all concentrated in one space. Instead, I could take that pot of energy and I could separate it out across 5 equal areas. Those 5 equal areas are all holding 1/5 of that amount of energy now. They're all equivalent in energy, but each one's holding 1/5 of the energy. It's just more stable to do so. I've spread across that energy now. Instead of me holding all of that energy in my hand, say I shared it with 4 friends, now we're all holding some of that energy. Remember, these compounds want to minimize their energy. So if I can take that little pot I have and separate it out into equal energetically equivalent states, then I have increased the number of microstates. I've increased the disorder because now that amount of energy is separated across 5 areas, but I've also increased the entropy and made the system more favorable because the energy is dispersed out over a larger area. Increasing entropy is favorable. So an increase in entropy and positive entropy is favorable. We say delta S is greater than 0 or positive for the dissolution of a solute by a solvent. We're increasing the entropy. Think about sodium chloride. If I have sodium chloride, and I dissolve this in water, I now have sodium ions floating around and chloride ions floating around. That has increased the entropy. I've increased the number of states those are in. It's all floating around in water. But I've increased the disorder. Instead of one crystal of sodium chloride, I now have multiple ions of sodium chloride floating around. So delta S is greater than 0 or positive when I dissolve a solute in a solvent. Even if I dissolve something that's not going to break apart into ions, say I dissolve sugar or sucrose. Say I'm dissolving some particle that looks like a little star. If I have a bunch of little stars all packed together versus little stars throughout the system. It's just more disordered. It's an increase in entropy, and it's favorable. When most, not all, when most solutions form, the entropy of the system increases. Solutions are more random than pure solvent. Entropy is introduced in this chapter, but again, we will go more in depth in a later chapter. But you do need to understand the basics of entropy and understand that the more disordered that system, the more microstates, the more favorable it is for that system, for that solution to form. We also have energetics of the solution process. So a key principle here is that solutions form when the solute-solvent attractions are comparable to the solute-solute and solvent-solvent attractions. Exothermic enthalpies. Entropy and enthalpy are hard words for me. I mix them up all the time, so I apologize. This is enthalpy, as we learned in first semester thermodynamics, the heat of the reaction. So exothermic, remember, delta H is less than 0, is an exothermic solution, or exothermic system. If delta H was greater than 0, this is endothermic. So while delta S wants to be positive, delta H wants to be negative. So exothermic is favorable. What we're talking about here is these relative strengths of each other. So we've got solvent-solvent interactions and solute-solute interactions that must be broken apart. We've got solvent-solute that are forming. What is the overall energy of the system? So let's talk through a thought experiment here. I want to walk you guys through this process so you can kind of see what I mean by all of this. For a solution to form, I'm looking at the enthalpy or delta H of my solution. I'm starting off and I've got my solute and my solvent. What I want to form is my solution. What's the process involved? Well, first, let's talk about the delta H of the solute. Delta H of the solute is the amount of heat I need to put in to separate those solute particles, break apart their IMFs. Something's holding it together. How much energy do I have to put in to break that apart? So at this point, I am talking about breaking this. Then I go in and I look at my delta H of my solvent. I need to do the same thing. I'm trying to break apart IMFs from the solvent standpoint. Now I've got my separated solute and my separated solvent. Then I look at my delta H of my mixture. So these both take heat. This is an endothermic process. This is an endothermic process. Now I'm going to mix them together. I'm forming IMFs between solute and solvent. This is an exothermic process. It's going to release energy. And I form my solution. Delta H of solution is the enthalpy of solution or heat of solution and can be measured, but it's a measure of this plus this plus this, where this will be positive, this will be positive, and this will be a negative value. What is the overall delta H of that solution? If the delta H value is negative, it favors solution formation. If it's positive, it favors not forming that solution. Does that mean that it's not going to happen? No, solutions can still form even if it overall takes energy, but that's when your IMFs and your entropy comes into play. Here's a nice picture of it from your textbook as well to kind of see the same process we're talking about. So we've got, and this is showing endo and exothermic processes. So key principle here from Gen Chem 1. Remember bond breaking Sorry, I'm so used to writing in cursive and I forget that it's hard to see sometimes. Bond breaking or IMF breaking is endothermic, meaning delta H is positive. Bond formation which also means IMFs forming, is exothermic. Delta H will be negative. So this system here, sorry, I'm trying to get the marker to work. Exothermic, this one endothermic. Let's talk through them just like we did the last one. We start out here at our first step. We've got our solvent and our solute. First thing I need to do is separate my solute particles. So delta H of solute, how much energy does it take? And now my solute is separated. I know they don't look separated in the picture, but let's pretend they're separated. Now my solute is separated. I'm going to look at how much energy does it take to separate out my solvent. I separate my solvent particles, and those both take energy. Now I've got both my solvent and solute separated. I mix the two together, so delta H of my mixture. I form my solution, and I see what's my final answer here. My delta H of mixing is negative. Overall, delta H of solution is equal to delta H of my solute plus delta H of my solvent minus delta H of my mixture. And in this case, it happens to be that the delta H of the mixture overall released more energy than it took to break apart the solute and break apart the solvent. So therefore, it is an exothermic process. It gives me a negative answer. Here, I see that my solution ends with an overall net endothermic process because the amount of energy released here upon mixing was less than the amount of energy required to break out the individual pieces. Another picture just kind of showing the same concept, the heat of hydration. So if I have KF, solid, the amount of energy it takes to break up the KF into its individual pieces versus how much energy does it take to hydrate it. Hydrate meaning solvate, surround with water molecules. I see here that the delta H of solution overall is positive 2 kilojoules per mole. So it's actually costing me energy to dissolve KF. So why is KF soluble? If it costs energy, how or why do solids with a positive delta H solution form these solutions? Why is this happening if it's taking energy? This comes down to a concept that's called spontaneity or Gibbs free energy. Which we will study a lot more in the thermodynamics and free energy chapter later this semester. But a spontaneous process. What do I mean by spontaneous? Spontaneous is a process that occurs without outside intervention, meaning I put these two things together and it just happens. If I put potassium fluoride in solution, it will dissolve. Even though it's an endothermic process, it will dissolve. Why? We measure this with Gibbs free energy, delta G. Delta G is the measure of spontaneity of a reaction. Delta G takes three things into consideration. It takes in the temperature of your system, it takes into account the entropy of your system, and it takes into account the enthalpy of your system. What temperature are we at? How much energy is it taking or releasing? And how much disorder am I creating? Those things together will tell me is a reaction spontaneous or not. At constant temperature and pressure, a process is spontaneous if delta G is less than 0. If delta G is greater than 0, it is not spontaneous. And if delta G is equal to 0, we have reached an equilibrium. This equation we will see again. I call this your 5-star equation. It can tell me a lot. But again, delta S, change in entropy. This is your temperature in Kelvin. And this is your change in enthalpy. And this is Gibbs free energy. So, will a solution form? Well, when I look at delta G, the delta G equation, that will tell me if it's spontaneous or not, but I need to really think about this process. The delta H of the overall solution is equal to the delta H of the solute plus delta H of hydration. You can also say delta H of solute, delta H solvent, delta H mixture. These two things make up the hydration. If delta H of your solution is greater than 0 or equal to 0, the increase in entropy, disorder, or microstates drives the formation of a solution if it actually forms. If the delta H of solution is less than 0, the decrease in enthalpy and increase in entropy will drive the solution to form, no matter what. So energy or heat has been decreased, and disorder or microstates has been increased. And overall, the energy payment compared to the energy cost and the net. How much did I pay? How much did it cost me? And what's the net answer here? So the solute to solvent payment is the energy released. How much energy is released when that solute-solvent interactions were formed? If that is greater than the solute to solute and solvent to solvent interactions that must be broken apart, how much it costs me, as the system to pay. This is the amount I'm paid as a system. So if the amount paid to me is greater than the amount I paid, my solution will form. If the amount paid to me is equal to the amount I paid, the solution will form. If the amount paid to me is less than the amount I paid, the solution may or may not form. It depends on the solution. If it does form, however, though, it is due to an increase in entropy. Which is the disorder microstates. So energetics of solvation, again, delta H of hydration. This is the same as delta H of the solvent minus delta H of the mixture. Delta H of your solute, how much energy do you need to separate the solute particles? It's endothermic, delta H is greater than 0 because you're breaking interactions apart. The delta H of your solute is the delta H of your lattice energy. Remember lattice energy from first semester? How much energy does it take to break apart a lattice? In delta H of hydration, or the enthalpy of hydration, how much energy is needed to separate the water molecules to make room for the solute particles to fit inside? This is an endothermic process. Delta H is greater than 0, plus the energy that's associated with the solute-solvent interactions that are formed, which is an exothermic process. Delta H is less than 0. A common exothermic reaction would be dissolving sodium hydroxide. Sodium hydroxide gets very hot when you dissolve it. When we make it in lab, when the TAs make it in lab, they actually have to be cautious of how hot it can become, and oftentimes have to use an ice bath, or not even an ice bath, a water ice bath as a heat sink to keep it safe so the glass doesn't break. So for example, if I dissolve sodium hydroxide, 1 mole of it, releases negative 44.5 kilojoules of heat. Negative meaning that it's been released, but 44.5 kilojoules of heat is released. A common endothermic solution is dissolving ammonium nitrate. It will dissolve. Oftentimes I have to just kind of swirl around, put some energy into it to get it to happen, but it gets very cold when it dissolves. And it takes 25.7 kilojoules of heat for every 1 mole that's dissolved. So how can you tell in the lab how this is happening? This is hot to touch. It's releasing the energy. This is cold to touch. It's absorbing the energy from the outside, from the surroundings, and bring it into the system. What about benzene? Benzene is a nonpolar compound. Benzene is a ring. You've got 6 carbon compounds with alternating double and single bonds, and each has one hydrogen attached to it to give it its 4 bonds. This is most definitely nonpolar. You'll also see this written like this. Benzene is nonpolar. So if I was to dissolve benzene in toluene, toluene is also nonpolar. Toluene, so this is benzene. It's toluene. Overall, there's no delta H of solution. It's just miscible. Delta H of solute, delta H of solvent, delta H of the mixture. There's no change in energy here. This is soluble. Or miscible, meaning that they will mix in all ratios. If I put benzene in water, water's definitely polar. I see a huge delta H of solution here, a huge difference. That would take a massive amount of energy. It's not soluble. These are immiscible. They don't mix together. Like dissolves like. Here's a nice chart from your book showing some different compounds and their solubility in hexane and solubility in water. Water is polar. Hexane, hopefully you guys can look at that and remember, but the hexane is nonpolar. Methanol is completely miscible in water. It's got a little bit of solubility in hexane because it does have a slightly nonpolar end to it. It is a small molecule. It's not great solubility though. 0.12 moles in 100 grams, not very much. Ethanol, completely miscible in both. Propanol, completely miscible in both. Why? If water and cyclohexane, or water and hexane don't like each other, and one's polar, now one's nonpolar, why are they soluble in both? It's because of this group here. This is what I mean by sometimes you can have a polar end and a nonpolar end. This end that I'm highlighting in purple is nonpolar. The end that I'm circling in blue is polar. That nonpolar side allows it to be soluble in hexane, while the polar side allows it to be soluble in water. Same thing on these two alcohols. Butanol and pentanol, we see are both completely soluble in hexane, but we see their solubility in water decreasing drastically. That's because the chain is getting longer. The longer that chain gets, the less it will be soluble in water because the less pull this little polar group will have on the overall molecule. The more this is taking over. So it really does depend on the overall structure of the molecule. Which of the vitamins below is the most dangerous if given in a large dose? Why? Which is the most soluble in fatty tissues of the body, and thus they retain in the body longer than water-soluble vitamins? What do we think? fatty tissues. What are fatty tissues going to be? Retain in the body longer than water soluble. That's suggesting to me water soluble, I know, is a polar compounds. That's suggesting, even if I don't know it, that fatty would be nonpolar. Looking at A and B, which one is going to give me more problems? Which one is more dangerous? The one that's nonpolar, because it's going to stay in the system longer. Looking at these two compounds, OH, CO, this group here, OH, 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 this is very polar. This has all carbons and hydrogens and carbons. This is nonpolar. So this is going to be the vitamin that's going to be the most dangerous if given large doses, because it's so nonpolar. It's going to stay in the fatty tissues of the body longer instead of being washed out with the water-soluble vitamins. And which substance in each pair is more soluble than water? Well, water, polar. So you need to think about what these structures are. And more soluble means more polar. Sometimes it's easier to draw these out. If you can see it quickly, great. If you can't, try drawing them out. CH3OH. That's definitely polar. CH3CHF2. It's also polar. Which one's more polar? It's smaller. This has this whole nonpolar chunk to it. That's bigger than the nonpolar chunk on this one. You could even say technically that it's kind of like this whole thing is nonpolar. This carbon is polar to these fluorines, but this only has just these little hydrogens here. So the one that's more polar is more soluble because water is a polar compound. Looking at this, if you draw this out, you're going to find it's a longer carbon chain. Called butane. Probably heard of butane gas. Versus CH3Cl. Which one's more polar? This one. Therefore, it is more soluble in water. If I asked you, say, hexane, C6H14, nonpolar, I would take the one that was more nonpolar or less polar. That would be soluble in hexane because hexane is a nonpolar solvent.